Many thanks to the organizers for giving me this opportunity to speak here. So what I'm going to talk about is some recent work with Nathaniel Berestiki, who is there, and Benoit Lallier, who is there, and the work is on some model of weighted random maps. So let me start by defining or maybe giving an overview of what's coming. So first I'll give you I'll define what the FK cluster model on graphs are, and then I'll define the model we work with, which is an FK weighted models on random maps, and I'll give some connections with some bigger conjectures at the background, which is the relations of these maps with Liouville quantum gravity and some other stuff there, and then I'll state the main theorem, and the main theorem is about finding out the exponents of the lengths of the loops and also the area inside them. And then I'll describe the main tool which we use, which is the so-called hamburger-cheeseburger bijection due to Sheffield. And then I'll conclude with the ideas of the proof, which gives us a connection of this model with certain random walks in cones, so which are we think of independent interest. So let's start with the model. So we have a graph, and we have some edge percolation on it, and what we do is we weight the percolation clusters by the number of clusters according to some parameter q. So we give weight q to every connected component that we have, and these are vertex connected components. And so this model comes with two parameters, p and q, and this parameter q is what separates it from just Bernoulli bond percolation. So for q equals to 1, for instance, you just end up with the edge Bernoulli edge percolation on a graph, and when q equals to 2, it has some connections with Ising models on graphs. You can construct a coupling which shows that these two models are really equivalent. And in general, for general q, you can find a coupling with the general q state Potts model on graphs. So the point p equals to square root q over 1 plus square root q is kind of special. It's called the self dual point, and it was proved by Beffara and Dumanel-Copin that at the self dual point the model is critical in the square grid. So this is a kind of a very interesting model to work on. And the model we are going to work on, okay, so this is the connection with the q state Potts model, and the model we are going to work on is on general maps. So here's a map. The map is given by the black edges, and the percolation cluster on it is drawn by the thick black edges on it. And so for every map we can associate a dual map, which is given by the red dotted lines, and I've drawn the dotted lines for the edges in the dual, which are there, which correspond to the primal edges which are not there in the percolation cluster. So, and I must emphasize that there is a vertex here, so we are really looking at vertex clusters. So for example, here in the dual graph, in the dual percolation cluster, there are actually two clusters. One is here, then the other one is the big one outside. And also in the primal one there's just two clusters. So for each for such a cluster on maps, you can define you can find interfaces between the primal and the dual vertex clusters, so which I've drawn in purple here. So for example, here in this example you have two loops in between the primal and the dual cluster. One loop is going around this primal cluster, one loop is going around here, and there is the third one here, which is around this single vertex dual cluster. So you can compute that the number of loops that you will get is always there is a connection between the number of primal and the dual clusters and the number of loops, and this is related by this equation. And in Z2, these loops, if you take your graph to be Z2, these loops are supposed to converge to a CLE kappa kappa in a scaling limit in the appropriate sense, which I'm coming to in a bit. So, and this kappa is related to q by this formula here. So these formulas will come up in the later theorems. So here's the model. So you take a plane map with n edges, and you have a submap which comes with a certain number of loops that I've drawn in the previous picture. So, and you weight every configuration by this formula. You give weight square root q to every loop in your model. And if you do some computation with Euler's formula, you get finally that your map is weighted by this formula, that you have q to the number of clusters and square root q to the number of open edges in your percolation cluster, and you have a certain extra weight to the number of vertices. And if you think about it a bit more, you will realize that this is the self-dual model, FK loop model on a random map, on the random map setting. The fact that it's self-dual is really clear from this formula, that if you look at the duals, the number of the loops are between the primal and the dual vertex clusters. So this model gives you a way to define. So this model is a critical statistical physics model on a random map. So you weight every map by a certain number of configurations, and in the end, these models are very important because they sort of serve as certain. So these models serve as discrete approximations to certain quantum gravity surfaces, which I'm coming to in a bit. So for this model, let me describe to you what certain special cases. So when q equals to 1, as I mentioned, this corresponds to H percolation on a random map, and this was studied before by many people. So this when q equals to 1, this will correspond to the uniform map, which Gregory was talking about in the morning, or Marie or Timothy was talking about after lunch, and studying percolation on such maps or just these maps themselves. There's a huge bunch of literature on them. You can compute the scaling limits, you can compute the local limits, you can study what's the critical percolation and how the scaling limits of the clusters behave and things like that. And and when q is 0, these maps correspond to spanning tree weighted maps, which means that you do not give any weight to the loops. So the things that the percolation clusters that you give weight to are just spanning trees. And so q equals to 0 was studied before by Mullins and Bernardi, and it has a very nice description, very nice and simple description, which I'm coming to in a bit. So this is this is what these maps are supposed to describe. So you take a surface with a Gaussian free field on it, which is an object which is a generalization of Brownian motion, but in sort of 2 dimensions, and you take a measure defined like this, where you take e to the gamma times the field. So this measure is not easy to describe, but there have been a large amount of work which goes back to Kahan's chaos theory, which helps you construct these measures for log correlated fields, and then there's been work of Duplantier Sheffield to develop these measures on general surfaces. So the models we talk about here in this talk are supposed to describe one of these surfaces in the discrete setting, and this gamma is going to be a certain function of the weight q that we take in this model. So, and this gamma is related to something called a central charge in statistical physics literature, and this is related to what kind of statistical physics model that we are taking. So here's the connection. So you have, when you look at this model in the scaling limit, so this is not similar to the scaling limit, the metric space scaling limit, which was described by Gregory in the morning. This is somewhat different. So you take your map and you have to somehow embed it conformally in a plane in a nice way. So there are several ways to do that. And one natural way which people have studied is the circle packing, or you can use the Riemann uniformization theorem to sort of to embed to find a conformal map between the Riemann surface described by your map, which you form by just gluing polygons, and you embed them in the plane in a nice way. And somehow if you take a scaling limit, so the conjecture is that whatever if you take some nice conformal embedding, then in the scaling limit they are supposed to converge to this CLE kappa decorated surface quantum gravity surfaces, and the parameter gamma is going to be related to Q by this formula for this particular loop model. So that's the background picture, and we will so in this work we compute some exponents and give some small evidence as to why this sort of conjecture might be true. Okay. So, and there is also another thing which is very interesting in this line of work, which is this so-called KPZ relations, or the Khrishnit-Polyakov-Zamolodchikov relations. So what this says is that if you take a subset of the plane which the certain scaling exponent x, so you have so in the Euclidean setting you take some random fractal set in your plane, and you compute and so it's best described in this sort of a discrete analog of this equation. So if you take a random map model of a huge size, and let's say take any fractal set which has to be independent of the underlying field, and let's say you take the percolation exploration interface. So for q equals to 1, the interface which is between the primal and the dual cluster, and let's say that in a map of large size, this interface is of size n to the 1 minus delta. So this delta is the so-called quantum scaling exponent. And in the Euclidean setting, you have a similar interface. If you take a box of volume n, so you have a square root n by square root n box, and let's say the exponent is given by n to the 1 minus x. So this is for so the percolation interface is just an example. You can take any reasonable fractal set in these two worlds. One is the quantum world and one is the Euclidean world, and then x and delta are supposed to satisfy this remarkable quadratic equation, which essentially says that if you know the exponent in one world, maybe in the Euclidean world, you can deduce this in the quantum world, or say otherwise, if you know this in the quantum world, you can deduce this in the Euclidean one. So these relations are extremely interesting and might be and should be very useful to compute exponents. So here's the main theorem that we prove. So you take our model of maps, which is weighted by square root q to the number of loops, and so let's say you have your finite maps and you have a certain number of the loops in between the clusters in these maps, and let's say you uniformly pick one loop, and so the first assertion is somewhat follows from previous results of local limit theorems for this kind of models, which I'm coming to in a bit. So what should be taken? So what we sort of start with here is that these typical loops converge to a certain map L. So by this I mean that if you just look at the triangles traversed by the loop, they will, and look at all the triangles inside them, for example, or maybe at a certain distance around them, they will converge to a certain finite map L with a certain loop. And also but the main statement of the theorem is the following, that if you look at the length of the loop, then the scaling exponent is given by this number 1 over p naught, and the size of the map inside it is also given by the exponent of the size of the map inside it is given by p naught, where p naught is related to q by this formula, and which essentially is equal to kappa over 8. in our result we have this dependent on epsilons, and simultaneously when we were finishing up this work we learned that Nguyen, Mao and Sun from MIT have similar results of similar exponents, but with regular variation here instead of these epsilons. But we think that our results are the methods used were completely different, and our results have some connections with random walks on cones, which we think are of independent interest. And it seems that this work is a bit more technical than ours, but although they gain a lot more, of course. Okay, so here's the two things that we prove. So for q equals to 1, which is the percolation case, we get that P naught is 3/4, and in fact this matches with previous work due to Kuvian and Korchemsky, where they find out the exponent of the length of the loop through the root. So there the condition on some event. So there they look at the loop through the root, which makes the exponent lose 1 here, because we are picking a typical loop, and when we look at loops through the root, that means that we are biasing the loop by its length. So modulo this bias, these results match. So let me now describe what's the main tool in proving this theorem. And before that, let me ask if there is any questions on this theorem. Okay, so here's the main tool is the so-called hamburger cheeseburger bijection, which goes back to Sheffield, and before that some work due to Mullins and Bernardi on spanning tree weighted maps. So this is the case q equals to 0 when you do not have any loops. So you have this class of maps weighted, where each map is weighted by the number of its spanning trees, and so what this bijection says is that there is a bijective correspondence between these weighted maps and excursions in the positive quadrant of Z2. So what is this connection? So before describing this connection, we are going to go through another sub connection, which is a connection with a certain inventory process in a factory. So let's say it's a burger factory, and you have two kinds of burgers, cheeseburgers and hamburgers. And so what you do is in the burger factory you produce cheeseburgers, and I'm going to denote that by a circle C, and if you produce a hamburger, I'm going to denote by a circle H. And when the customers come, they order either a cheeseburger or a hamburger, which I'm going to denote by box C and box H. So what happens in this factory is that you keep on producing cheeseburgers and hamburgers, and certain customers come and they ask for cheeseburger or hamburger, and what you do is you have a single stack. There's not much room, so you have a single stack of burgers, and so when you produce something, you just put that burger on the top of the stack, and if a customer comes and asks for the cheeseburger or a hamburger, you take the topmost burger that you have in your stack and you give it to the customer. So if you have, let's say, 2 cheeseburgers and 1 hamburger, and a customer comes and asks for a cheeseburger, you take the topmost cheeseburger from your stack and you give it to them. So what has all this got to do with maps and spanning tree weighted maps? So here's the picture again, where I have now a spanning tree in my map, which is given by this. So the map is along with these black dotted lines, that's the whole map, and I have a spanning tree in the map, and I have a dual map which is given by these red edges. Now I now have the loop which forms the interface between these two clusters. Now I have a single loop because it's a spanning tree, and since it's a spanning tree, the dual cluster is also a spanning tree. Now what I've drawn is I've drawn these additional green edges in the face between the dual vertex and the primal vertex. So here's so for example, in this particular face, I have drawn the green edge from this red to all the black vertices, and this divides my face into triangles. And moreover, for every edge here we have a quadrangle like this. So for this edge I have a quadrangle like this. Now, so observe that the triangles are of two types. There is the there is the triangle with a black edge, which we are going to call a hamburger, and there is a triangle with the red edge, which corresponds to the dual edges, which we are going to call cheeseburgers. So, and every time we encounter a face, we are going to associate it with production or an order, depending on whether I have matched that particular face with a cheeseburger or I have just produced it. So an example will make things very clear. So here I have, let's say this is the root edge, and I have started exploring the map along this purple loop through here. So my first triangle is a red one, and it's not a match of anything. It's the first triangle, and I have associated a cheeseburger with it. So that's my first cheeseburger in my stack. So the next one is this triangle that's associated with the red edge, another one. So that's another cheeseburger, and that's so I have another cheeseburger in my stack which is produced. So I go on, I produce another cheeseburger. Then here you see there is a triangle with a black edge. So now that's a hamburger. So I produced another hamburger. Now I have produced another black edge and another hamburger. Now you see that I'm going to record this by putting these symbols as well, which correspond to cheeseburger or hamburger production. So I have now produced 3 cheeseburgers and 2 hamburgers, and this sixth one here is a match of number 3, which I have already explored. So I have completed this whole quadrangle here, and so I have taken away the cheeseburger which was there before, this one, and given it to the, so this will correspond to a cheeseburger order, and so I have written a box C here. Okay. So finally, when I complete exploring this whole thing, what's going to happen is we are going to match every cheeseburger with its match, or every hamburger with its match, and when we end up so this is a spanning tree, so we will be back at the root, and we end up when we end up being at the root, then there will be nothing left in the stack. And moreover, what's true is that there won't be any orders coming in which will not be which are not fulfilled. So for example, when there is an empty stack, a customer can come in. So for example, from this case on, there can be 2 customers demanding cheeseburgers, demanding hamburgers coming in, and there is a third customer coming in which also demands a hamburger, but there is no hamburger in the stack produced yet, and so that order will go unfulfilled in this case. But since this is a map, there will when I have an order, it must come with a production before. So this means that this sequence won't so this won't happen in this sequence, that there is an order which remains unfulfilled. So in the end you get some sequence like this, where the number of productions actually match the number of orders, and also the number of productions of each type and the number of orders of each type also match, and somehow they grow independently in this model, because there is I mean, you can take any sequence of cheeseburgers and hamburgers of equal number of productions and orders and match them together to get this. Now, so what I mean by this is that if you associate with each order a right step in Z2 or an up and down step for the hamburger productions or orders, you are going to get an excursion in the positive quadrant. So here you will start from here, go here, and then come back to the origin. So that's the bijection with excursions in the quadrant and tree weighted maps. But we're interested in an extra parameter called Q. So we introduce so this was introduced by Sheffield, that we introduce some order called the fresh order. So what is this? There is a new kind of customer who comes in and orders the freshest burger that is on the stack. So you have a stack of burgers, and if you have nothing, that order goes unfulfilled. But if there is something, you just give the topmost one. So he doesn't care whether it's a cheeseburger or a hamburger. So that's what is meant by the fresh order. So you had this, I have this, how does it correspond to this loop model? So I have this configuration. Now let's say I have this, I replace this box H by a box F here. Now what I'm going to do in that case is that this box H previously corresponded to certain a hamburger triangle and its match. It's this one. So this was the match, and this was the original triangle. It's the last but one order. So I started here. So this is the last but one order, and when I have an F symbol, what I'm going to do is I'm going to just flip the type of the quadrangle. So every quadrangle is either ham or a burger or a cheeseburger type. So I flipped it. I've made it into a dual triangle and its match. So now I have a dual edge like this, and this has broken down my percolation configuration into it's no longer a tree. It's divided it into two components, and in fact it can divide it in, and you can have cycles. You end up with cycle in the dual configuration. So what I'm going to do is I'm going to give some weight to this fresh orders, and this weight should correspond to the weighted loop models that you get in the end. So as you can see, when I introduced an F, I've divided the loop into two loops. So the number of number of F symbols that I have plus 1 will correspond to the number of loops in the model. So here's the thing. So you have you take a sequence of variables which takes values in this set of symbols, and you put certain probabilities to each of these symbols, and let's say they're IID, and you condition on the fact that so what this means is that all the orders are fulfilled, all the productions are fulfilled, which means that there is an order corresponding to each production, and there is no order coming in for which we don't have any burger left in the stack. So when these two conditions are satisfied, all these so you can think of this as a reduction of words with certain relations which you can easily guess, and what this means is that you condition on these relations to be empty set. And finally, since there is a weight of p over 2 corresponding to every fresh order, you see that so for the production I have no weight coming in, and for the orders there is a weight of 1 minus p over 4 coming in from the C or the H, but the total number here must be n, and from here you can deduce that the weight is actually the ratio of these two numbers, and of course this is also 1 minus p over this quantity to the number of loops, and it makes sense to to set square root of q equal to this number. So that's how we recover our finite model. So in the finite case, if you want to weight something by square root of q, you compute the right p, and you take a sequence like this with these probabilities, and you look at the conditional distribution with this conditioning, and that should correspond to a map, to a weighted loop model on maps. Okay. Now what we want to do is we want to take this local limits of these maps. So what this means? So what does it mean to have? So what's the local limit? So basically you look at two maps. You define a topology like this, that you say two maps are close if the combinatorial ball of radius r in one of them is close to the combinatorial ball of radius r in the other for a huge r. So more the r, the larger the r that you can find such that these two balls are close, the more close these maps are. So basically you're looking locally near the root. It's an infinite volume limit, and so and so what you get in the end for this model is that the local limit does exist, and this you can find out from this bijection with these finite words with these probabilities. And what you really need to show to get these bijections is to show that if you take a uniform point from this sequence conditioned to be empty, then you end up with by infinite IID word locally. So locally you get IID with IID symbols with the probabilities given by these numbers. And so what you need basically for this is to show that this probability is sub-exponential in n. That's enough to get this convergence. Now, so it was also proved by Chen that these maps have exponential tail, and hence they are recurrent from the works of Gurel, Gurevich and Nakmias. But what we are interested, so one thing to observe here from this is that from this bijection is that in the IRD sequence, every burger has a match. This you can deduce very easily because it's an IRD sequence. Now, so what this means is that there is no triangle in the map which doesn't have its brother in the infinite limit. So when you have this infinite model, it's no longer clear that if you go forward in your sequence of IRD word, you have the same behavior as you go backward. So here's a way to sort of maybe explore this infinite map. So let's say my root is here. So here's my IRD sequence starts from here, and I go to the past. So I go look at the left sequences, and here's a possible way to explore this map. So let's say I start with a hamburger production. Now notice that this hamburger production is being produced just to the left, just at the position -1, which means it's going to be fulfilled at some place in the future. So if we keep exploring the past, this triangle is never going to get fulfilled. So we note this, and we sort of shade it to be gray. Then we go to the next one. Let's say it's a C production, and we again notice that it's going to be eaten up in the future. We shade it to be gray again, and we draw this red triangle, and we go on until we reach the interesting point, which is this F symbol. Now notice that this F symbol, if we know only up to this, then we don't know what the F symbol corresponds to, because you need to know what this fresh order corresponds to in order to know whether you will draw a red triangle or a black triangle. And in order to know that, you have to go a bit further in the past, and you see here that this F actually fulfills this C production. So this F is actually a red. So this F in the tree description, it's a red triangle, but when you flip the edge, you will end up with a black triangle. So here's what it is. So you draw the red one, then you complete these two triangles form in between this F and its match, and then finally you end up finally you have this C. When you complete the loop and you flip this red edge to be a black edge, and you end up and you leave this loop aside, and you go on exploring the other triangles here. So that's how you form the loop. And as you notice that what you see between an F and this C is what more or less corresponds to this loop here, and the triangles corresponding to this loop. So if you want to study the loop, this gives you the hint that you need to look at the F symbols and what we call the envelopes of these Fs, or what this corresponds to all the symbols between the F and its match. Okay, so this so you can make these observations from this infinite IRD sequence, that okay, every F symbol comes with an envelope, which is all the symbols between the F and its match, and so F symbols are of two types. One is the CF, which means that the F is fulfilled by actually cheeseburger production or an HF, and so when you have a CF, this means that so this corresponds to a dual cluster surrounded by a primal cluster, and vice versa. So and in a CF type loop, you can make this observation that in an envelope you can have further F symbols and further envelopes nested between them, and all the CF type loops nested in the envelope of this CF type loop are going to be outside. So if it's of the same type, then this loop is going to be outside the loop of this envelope, and if it's of the HF type, then it's going to be inside. So you can study this sequence and make these observations, but finally you realize that the C and the H are interchangeable. So somehow if you study the number of triangles in the envelope, you almost deduce what's the total what's the area that you enclose in the loop for this f symbol. So also more or less you can convince yourself that everything boils down to finding out the number of triangles that you can get between an f and its match. So okay, so you can play with this even further and make some more deductions. So what you get is so let's say you have a CF type loop, loop that you have encountered when you were exploring. So you start with a C, and then you have done your exploration to reveal some map. There will be some H orders left behind in the reduced word for the F symbol and its match. So those will correspond to the boundary of the map that you have explored so far. And finally, when we are going to close up this F symbol, you are going to leave a loop behind, and that will correspond to a certain portion of the map which we call the bubble. And what you can find out from our methods, it's not a priori clear, but what you can deduce from our methods is for any q, the boundary of the bubble is roughly square root of the volume. Now this is a universal behavior. This is independent of the parameter q, which we think is interesting. And further you can verify the KPZ relations. So the boundary of this bubble corresponds to this. So you have a bubble corresponds to a cluster, and there's the outer boundary of the cluster that you can fill in, and this outer boundary is supposed to be described by a parameter by an SLE with a dual parameter. And so using this relation we can use the KPZ formula as I described earlier to find out that the dimension of the dual SLE is this, which matches with the Befara's computation. So this computation that we do sort of satisfies the KPZ relations in some sense. Also, when you further look into this, you see the structure of the clusters emerging. So when you have a bubble, you leave behind some portion of the map, and then you go on exploring. Then you have a certain bubble which you leave behind certain portions and things like that, and then you grow a dual the dual clusters at the same time, and they are sort of interlinked with each other, and you sort of get a loop tree structure. So a loop tree is a tree where you replace a vertex of a certain degree with a cycle, and for percolation this was these structures were studied by Nicola and Igor, and the scaling limits of these objects were computed, which corresponds to a certain continuum loop trees, and you have this growing interface if you go to the past in between these two loop trees, and this sort of relates to this recent work of Miller and Sheffield on marriages of trees and stable trees and so on. So you can also deduce another thing from this picture, that when you have explored n triangles in the purple interface, the volume of the map, the total volume of the map that you reveal is roughly related by this relation. So the boundary, which is the length of the purple one, the purple interface is it's the volume to the power p naught. Now, okay, so here we find the connection between the boundary and the volume depending on q. So this is the total length of the interface, not the outer boundary, and this delta L is supposed to converge to this to an SLE kappa, and again we can do a similar computation through KPZ and recover that the dimension of the SLE in the Euclidean setting is 1 plus kappa over 8. So these results verify KPZ in general. Those are the things we can recover from this theorem, and these methods. And I'm going to spend the remaining time in describing how to get this exponent of the length of the envelope, and you can somehow deduce everything from there. So to do this, you first so this relies on a theorem which goes back to Sheffield, which I'm going to state in a bit. Before that, I need some definitions. So you first convert all the fresh orders to either a C or an H. That will give you a certain sequence of either C or H, and then you can define this this quantity, which is the algebraic count of burgers. So you count the number of orders and the number of productions and the number of orders, and you can look at the difference, which means, so this is basically a simple random walk, because the probability of seeing a C or an H is half, and the probability of seeing an order is also a half, just by definition. So this is just a simple random walk written in a fancy way. And you can also look at the discrepancy function, which is the number of which gives you the difference, the algebraic difference between the cheeseburgers that you have on the hamburgers that you have. So it's sort of counting. It's basically counting the number of hamburgers or a cheeseburger, but you have given it a linear transformation, and you have and you look at these quantities instead, specifically because this makes this well, one of the reasons is because this makes this quantity very simple. It's just a simple random walk. So you know that in the scaling limit you want to you get a Brownian motion, and you want to take a scaling limit of these objects. So here's the theorem of Sheffield, that if you fix this parameter alpha to be 1 minus 2p, then this when rescale, these quantities converge to independent Brownian motion, independent standard Brownian motion on the in 2 dimensions. And so there's this quantity alpha here, which says that in the discrepancy the variance of the Brownian motion is related to the parameter p by this quantity. And here you notice the max, which means that when p is at least a half, this alpha becomes 0, which means that the discrepancies becomes small o of square root n. And this somehow you can guess, because when p is large, that means that there are more fresh orders, and you sort of do not distinguish between cheeseburgers and hamburgers more. So and so you basically guess that the number of the discrepancy between them should be of n to the 1/4 order. But anyway, so the theorem says that in the end you get a 0 when p is greater than half, and we will focus on p is less than half throughout the talk, because that seems to be the more interesting regime. So there is a phase transition at p equal to half, as I mentioned, and one of the main things that goes in the way of proving this theorem is that when you have an IRD sequence and you look at the first n symbols and you reduce them according to this order and production, you just match every order with its production, then the number of f symbols that you get is much smaller than square root of n. And these f symbols are responsible for all the correlations between certain blocks of if you try to prove this theorem, what you would do is you would divide it into blocks and somehow prove that at the scale of square root of n they are somehow independent. And to prove this, the main idea is to show that the number of f symbols is not that much in the reduced world, from where the correlations come, and the correlations somehow vanish when you scale by square root n. So what this means is that so this also tells you that you can so you can think of this infinite word to the left as somehow an infinite stack of burglars, because there will be an infinite number of orders if you look at all the past symbols. And somehow what this says is that since the number of f symbols grow like square root or smaller of square root of n, the correlations between the past and the future do not matter much. You can condition and you can still have a CLT for the first n symbols. Okay, so we go back to this problem of finding out what is the length of this envelope, and so we look at this C and D, and we'll think of it as a walk in this grid, where I have rescaled the D to be 1 over square root alpha. So you have this elongated grid, and you have a certain angle here, which you can directly compute. It's tan inverse 1 of square root of alpha. It's an explicit function. Now when you want to know when you want to understand the probability that you have a huge F envelope, this means that you start from here and you ask the walk to you ask the walk to come back and escape from near the origin point. This is because when you hit one of the red axes, that means that the discrepancy and the algebraic count becomes the same. So this is sort of the y equal to x line in this grid. But so when you have this, that would mean that the reduced word looks like either all cheeseburger or productions or all hamburger productions when you are on this axis. So which means that if you start with a C production and you have all C's, then you cannot then if you start with a cheeseburger production, then and you are on a point on the axis which corresponds to having a lot of cheeseburger production, then you cannot have an F here which will eat that particular C, because F means fresh order and the burger must come to the top of the orders, top of the stack to be eaten by fresh order. So basically, but if you are in the other axis and you have a lot of H symbols, you can still be eaten up by a fresh order. You can still so when you are in this reflected boundary, that means when you are in this thing, you can have some cheeseburger orders here which we can ignore because we have because this cheeseburger which we can ignore because these cheeseburger orders won't eat up this H, and you can think of this walk as sort of reflected in this reflected boundary, and somehow you want to end up near the root in the end. So if you want to compute this probability, you somehow need to compute the probability that you start from the origin here and you reflect it on the reflected boundary and you come back to the origin, and you escape this cone through the origin, not through this other red wall. So you can ask a similar question with Brownian motion because these walks are approximated by Brownian motions, or that's what the scaling limit result says. So you can consider a reflected Brownian motion in the cone with a certain reflection angle. So and you want to ask, well, if you start a Brownian motion from this ball and it's reflected with this particular reflection angle, and you ask what is the probability that it exits through the tip in the end after a long time. So basically we need to compute that. So when t is the exit time of this reflected Brownian motion from this cone or this particular ball of radius 1, and you ask what is the probability that it exits this cone through this particular ball. So you can start thinking about this with the toy model of a non-reflected Brownian motion. So assume that there is no reflection boundary here, so you just have some Brownian motion in a cone, and you're asking what is the probability that it exits through the tip of the cone after a long time. So to do this, the first idea is to that you might think of is to construct somehow a martingale in this for this Brownian motion, and for that you need the harmonic functions in this cone, and you especially you want a harmonic function with zero boundary condition on this cone. So this is this function. You can sort of somehow derive this function by looking at the function in the upper half plane, which is just the imaginary part of z, and you take the conformal angle mapping the upper half plane to this cone, and you end up with this particular function with zero boundary conditions, and you notice that this h evaluated along the Brownian motion is a martingale. So if you want to know what the probability that it spends a long time in the cone, you can divide this event roughly into two events. One is that it goes up to a distance square root n from the tip, and the other is that from there it comes back and escapes through the tip of the cone. So for the first part, you have this martingale, so you can just use Gambles ruin, and you can deduce that this probability is roughly given by n to the minus p naught, which is where p naught is pi over 2 theta naught. So p naught in our theorem you can compute that it's given by this quantity pi over twice the angle, And for coming back, you can use the other brother of this harmonic function, which is r to the minus pi over theta naught, and this is also with zero boundary conditions. And you somehow using this martingale, you get that you get another exponent n to the minus p naught. So all over, if you want this probability, it's roughly n to the minus 2 p naught. So this is for the unreflected one. And so the basic idea which I want to drive home is to construct these harmonic functions with the right boundary conditions. Now, if you think about it, if the reflection that we have, so if you remember that the reflection we had a certain angle, and if you think that the reflection was perpendicular, then you can somehow look at a cone with double the angle. So you had a cone, and you had this reflecting angle. Now, if the reflection was perpendicular, then you can just reflect this cone to here, and the problem would reduce to a problem of exiting through the tip of the cone with non-reflecting boundary, and which I computed in the last slide. But somehow, if you do this computation, you end up with the same exponent, but that doesn't give you a proof because the reflection angle is not perpendicular. It's with some angle. So in the end, what you want is you try to compute the harmonic functions with this reflected boundary conditions, where you have a certain vector v naught along which you have the reflection. You need to enforce this extra condition that the dot product is 0 for these harmonic functions. So you do the computation, and you find out that you have two functions which have one. So for the going out part, you have a harmonic function which is r to the power 1, and for the coming back you have this exponent, and finally when you add them up, you end up with the same p naught somehow, which we think is a little miracle, but you end up getting the right answer in the end. So, and the last bit is which I don't have much time to go into, is to approximate these Brownian motion heuristics for this particular walk. It's not a simple random walk. It's a complicated walk with lots of correlations. But somehow the idea is to look at a large faraway x, and you divide the walk into chunks of steps, where you look at the walk at times when it exits the ball of epsilon times the distance from this route, from the origin of the cone. And so when you divide it into these blocks, you can approximate these walks by CLTs, and the exit measures are given by approximations of the Brownian motion. Okay, and this is somehow the heuristics of the bound of the bubble isoperimetry, which says that when you are in the cone for n steps, the number of times you sort of reflect in the boundary is roughly square root n, and this gives this bubble isoperimetry. So you can deduce all this from the Brownian motion heuristics. So in the end, we get all this. We can use this exponents for the loops to deduce our theorem for the length of the loop and the area inside. Okay, thanks a lot.
So this works for a particular model of uniform planar map with FK model on the map itself. Is there any hope to get universality, auto bijection, similar stuff for other kind of planar maps?
So for these models, you can somehow triangulate it to get a triangulation, but it's sort of related to the triangulation model in a slightly complicated way. But it's not a uniform triangulation. But one can try to adapt the peeling process for triangulations and see if we can find out a connection between this bijection and the peeling, and somehow develop the thing. But there is hope. I don't think there's no hope, but should be able to do it.
Yeah, so let me ask a related question. Has anybody looked at what happens?
A bit louder.
Has anybody looked at what happens when you put in an asymmetry between the burgers and the hamburgers?
An isometry?
Yeah, an asymmetry. So when you're taking them with 50-50 probability, what if you take them with 60-40 probability?
It gets a bit nastier, but there is some work I think of Chen there. I think there is a student of Nicola who's been working on this kind of stuff. So maybe he's the right person to ask this question. But I think it gets you off the critical, but certainly it's an interesting question, of course.
Okay, thank you again.